Alright, so today's topic, probably going to be the only topic of this video, is I don't know how to say this, these names, harish-chandra, it looks like. I don't want to be too presumptuous here. And the theorem states for lambda and mu and h star, if their characters match, then they are, what was the term we introduced for it last time? It was linked. If the characters match up, then we're linked. Technically, I believe the theorem is saying that the two are equivalent, but we already showed that if our roots are linked, then their characters matched last time. And so the rest of this is going to be the proof, I believe. So we start out fixing a basis of L. Say hi from 1 to L, and then x alpha, y alpha for alpha greater than 0. The notation there is kind of messy, but you know where I'm at. Where hi is equal to h alpha I, and delta being the collection of alphas. Construct a Poincare-Birkhoff-Witt base for the universal algebra of L and the universal algebra of H. Relative to an ordering. That's not even an O. In order, putting the y's, then before the hi before the x alpha. Define a linear map key from the universal algebra of L to the universal algebra of its H by sending each basis monomial in the collection of hi to itself and all others to 0. Now, if V plus is a maximal vector of the irreducible module V lambda, which I'm going to write out explicitly, for lambda and h star, consider how an element z in our fancy thing from last time acts on V plus. A monomial of the product of some y alpha of our y alpha to the I alpha times the product of our hi to the ki times the product of our xi alpha to the j alpha, for which some j alpha is positive, is going to kill v plus, while one for which first off all j alpha is 0, so this x term disappears, and some I alpha is positive, sends v plus to a multiple of itself, and then to a lower weight vector. From this, the only monomials which contribute to the eigenvalue chi lambda z are those for which all I alpha is 0 is j alpha. Thus, from this we get, with chi's above, that with xi is above, that chi lambda z is equal to lambda of xi of z for z in our thing. And xi is just that just keeps the elements in H. And note that lambda extends canonically on from a domain of H to domain of the universal algebra of H. And notice that the restriction of chi to our fancy thing is an algebra homomorphism by this. Alright, that I would notice that chi restricted to this is now an algebra homomorphism. Originally it was just a linear map. Now, this incorporates delta. We need to see how that happens. Now send each hi to hi minus 1 and extend linearly to a map H to the universal enveloping algebra of H. This is a Lie algebra homomorphism with all the products just being 0. So and so extends to a homomorphism eta from the universal enveloping algebra of H to itself. With this eta being an automorphism. Now you can just add one back to get its inverse. Now, let psi from this thing to the universal algebra of H be the composite homomorphism of eta composed with the restriction of xi to whatever this letter is supposed to be. Recall that in this context our delta is the sum of the fundamental domain weights in fundamental dominant weights, sorry, not domain, in our lambda. So the delta of each hi is 1. Thus we have a long equation, which we need to write a new line, that lambda plus delta of hi minus 1 is lambda plus delta of hi, of course, minus lambda and delta on 1, which is going to be lambda of hi plus 1 minus 1, which is of course lambda of hi. Thus, lambda plus delta of psi z is lambda of xi z. Alright, and combining this with our previous formula up at the top there in the first line now, we get that chi lambda of z is lambda plus delta of psi of z. Now, we're going to let lambda be integral by our previous corollary, all the conjugates sigma of lambda plus delta agree, oh that was real baddie at the end, at xi of z equivalently our letting mu be lambda plus delta takes the same value, same val at all vowel conjugates of psi of z. From that, the file group must fix our psi of z for z in our fancy set, and we may replace universal enveloping algebra of H with the symmetric algebra of H, as H is abelian. Thus, C maps this into the elements of the symmetric algebra fixed by the Weil group. Now, from this, we get that for all lambda in the dual of HSR, chi lambda z is lambda plus delta of psi of z for z in this. Now, as c of z is the Weil group invariant, the right hand side remains when replacing lambda plus delta with sigma of lambda plus delta. As chi lambda of z is chi mu of z if lambda is linked to mu. This is our previous corollary, but for all lambda mu in H star. As we remarked earlier, I believe, hopefully. Now, we now know that chi lambda of z is lambda plus delta of cz for all lambda in H star. Suppose that chi of lambda is chi of mu. Then we know that lambda plus delta and mu plus delta agree on C of this, which lies in the symmetric algebra of H invariant under the action of the Weil group. Now, to prove our theorem, we need lambda plus delta and mu plus delta conjugate under the Weil group. Which is equivalent to showing that chi of the set is actually equal to the elements of the symmetric algebra invariant under the action of the Weil group by a lemma. And that lemma states that if we have two elements, two functions on H lie in distinct Weil orbits, then lambda 1 and lambda 2 take distinct values. We need a new page. Distinct values at some element of the symmetric algebra of H invariant under the Weil group, which is, just to recall, equivalent to the polynomials on H star invariant under the Weil group. And the proof only relies on the finiteness of the Weil group. Now, choose some polynomial n8s of H at which lambda 1 does not vanish but at which all other vowel conjugates of lambda 1 and all vowel conjugates of lambda 2 vanish. Add the images of this polynomial to get an element of sigma h to the w at which lambda 2 vanishes and lambda 1 doesn't. Now, we need to show now for this. We aim to show that C maps this onto S of H W. Now, recall that S of L may be identified with the space of symmetric tensors in I of L, complementary to the kernel of the canonical map from I of L to the universal enveloping algebra of L. Let G be the inner automorphisms of L, which acts on IL. As S of L and J are stable, OJ is the kernel. Well, let's just call it as S of L and the kernel of pi are stable under the action of G. The linear isomorphism pi from S of L to U of L is actually an isomorphism of G modules. To note, by S of L G, the subalgebra actually of elements fixed by G by a, oops, that looks like 6, by a previous lemma pi maps this SLG onto the elements of the universal algebra fixed by G. And note that pi here is not a homomorphism, it's just a linear map. We now, so to overview, we now have SL of G mapping by pi to that mapping by psi to S of H to the Weil group, which is similar to the function from BL G are old theta to BH of W. Now we can canonically identify L with L star, H with H star, by the killing form, and with the actions of the interior automorphisms and the Weil group being compatible. This gives us a diagram of SL to the G, which is equivalent to BL to the G. Here we send this to this space by pi, which we then send from above to S of H of invariant to the Weil group. At the bottom here we send it to being invariant, B invariant to the Weil group, and we identify these two things with each other. Now note here, the map on the bottom is theta. And now it's worth noting here, does not quite commute. So the path you take will change the result. Now, let's look at an example here, it says, to help clarify things. Let L be SL2 of F with basis X, Y, H. The dual basis X star, Y star, H star may be identified with, if you work out this math, it ends up being 1/4 of Y, 1/4 of X, and 1/8 of H by the killing form. Now F. Lambda is the fundamental domain weight, which would make it half of alpha. Then here lambda identifies with H star, and of course then lambda square generates B of H to the Weil group. Now, lambda being the highest weight of the standard representation of L, by which I think they mean x being the right shift, y being the left shift, and h being flipping the y-axis on a two-dimensional space. From that we get the trace polynomial h star squared plus x star times y star equals theta inverse of our lambda squared under the identification of BL of G with SL of G. This becomes, the symmetric tensor 1/64th of h star h tensor h plus 1/32nd of x tensor y plus y tensor x. Now, pi maps this element to 1/64th of h squared plus 1/32nd xy plus 1/32nd of yx in our fancy set. Now, to calculate the image under our C, we rewrite this element in the Poincare break-off wet basis relative to the ordering yhx as 1/64th h squared plus 1/32nd yx. They have it here as 2/32. Well, that doesn't make any sense. That's got to be 1/32. They write it here as 2/32. I don't know why they'd write that as yx. Oh, and maybe that does make sense actually. 2/32 plus 1/32 of h. Theta send, that's not even a theta, that's like c. C sends this to 1/64th of h squared plus 2h and then eta to the Weyl invariant 1/64th of h squared minus 1. Reverting back to BHW, that's supposed to be the Weyl, right fancy. We get pi squared minus 1/64th. which is very much different than our previous result. So thus the diagram does not commute with the discrepancy measured by an invariant, hence the scalar 1/64th here, of the lower degree than the element, the starting element. Sorry about that. Thus, the diagram does not commute with discrepancy measured by invariant of lower degree than the starting element. So, this suggests how to complete the proof that C is surjective. It actually is a proof for SL2. So first we need to first we agree to identify BL of G with SL of G and BL of the file group with SL of the file group. Now, obviously, if the polynomial in SH is fixed by the file group, so are its homogeneous parts. Thus, we will lift homogeneous polynomials Oh, I hit the pen size all of a sudden. That's scary. Was it here? Polynomials to our fancy set by inducting on degree. Now, theta and the composition of xi on pi are essentially the same. Except we must rewrite the symmetric element pi f in the Poincare-Birkhoff width basis for applying our xi. Introducing new terms. If f has degree k, then pi f is a sum of terms x1 through xk in the universal developing algebra of L, So the new terms obtained by commuting how they form x1 times x1 through xj for j less than k. Our map eta, which sends hi to hi minus 1, has no effect on highest degree terms of polynomials in the symmetric algebra of H. So we can recover our original homogeneous element of S H W modulo lower degree terms when we navigate our diagram by theta inverse, then pi, then c, and c. By induction, the lower degree terms are images under C of elements of this set. And so we're done, and we're done with our proof here, and we're going to be done with our video. Next time, we're going to go over a couple things we kind of glossed over in here, and then maybe go on to some formulas that are important in this area, I guess. So look forward to that.